This video, we're going to briefly review some things that we've learned about basic sequences and their related series. So we're going to look at arithmetic, geometric, p-series, and telescoping series very quickly, and it's summarized in this table. So the first type is the arithmetic sequence and series. It's based on a linear function with a restricted domain to the natural numbers. Recursively, the formula of the underlying sequence is a sub k minus 1 plus m. Some people use d there. So m is the delta a, the common difference or slope. A sub k then non-recursively, explicit formula is mk plus a sub 0, where a sub 0 is a1 minus m. A finite sum of that series, S sub n, is the sum from k equals 1 to n of m sub k plus a0 in closed form, that is n times a1 plus an over 2. Or in terms of only n, m, and a1, it's n times parentheses 2a1 plus parentheses n minus 1 close parentheses m close parentheses over 2. The infinite arithmetic series always diverges to infinity if m is positive and to negative infinity if m is negative. The geometric sequence and series, that's an exponential function with only natural number inputs. A sub k is b times a sub k minus 1 for your recursion relation. A sub k is a sub 0 times b to the k, or a1 times b to the k minus 1. A sub 0 is a1 divided by b. B is a sub k divided by a sub k minus 1. It's the base or common ratio. Some people use the letter r there. It has a constant base and a variable exponent. So the sum of the first n terms, sum from k equals 1 to n of a sub 0 b to the k, is a1 1 minus b to the n over 1 minus b. The sum of infinitely many terms is this b to the n goes to 0, so it's 1 over 1 minus b times a1 if the absolute value of b is less than 1. So it converges if absolute value of b is less than 1, but it's going to diverge otherwise. A p sequence and p series is basically a power function with the domain restricted to natural numbers. So that's a sub k equals k to the p power. Notice that the limit of the underlying terms there is 0 if p is negative, 1 if p is 0, and infinity if p is positive. This is a variable base and a constant exponent, power function versus exponential function up here. We don't have a nice form for that, but I can tell you when the infinite series converges and when it doesn't. S sub infinity, the sum from n equals 1 to infinity of n sub p, n to the p. Let me change that to k's. I like to use. In my sequences, I try to let k be the variable for the underlying sequence, and then our counting variable for our sum here, and then our index variable. And then n is usually how many terms we add up, so it might be the top one here, but in this case, it's infinity. But anyway, the p series is going to converge if p is less than -1 and diverge if p is greater than or equal to -1. Notice how I've written this as k to the p, not negative p. So your book that you may be using may say negative p, in which case the conditions are a little different here. So specifically, p equals -1 is the divergent harmonic series. It's kind of the borderline there. We also have a telescoping series. A sub k is b sub k minus b sub k plus 1. So if you can somehow think of this as two parts, then when you sum from k equals 1 to n of b sub k minus b sub k minus 1, every other part of the b's cancels in the middle, leaving only the very beginning and end is b1 minus b to the n plus 1, so it collapses like a telescope. So then that's going to the infinite sum then will be b1 minus the limit as n goes to infinity of b sub n. So if b sub n exists, then this has a sum. So that's a quick review there of this. And so in particular, we know about convergent geometric series, and we know about convergent and divergent p series. Those are going to be used in our next couple of sections when we talk about direct comparison and limit comparison tests.